Okay. Hi again. This is Sean Horgan again. Can I just do a sound check? Mike, Shrant, Vignesh, could you just check? Can you hear me okay? One of you
Yeah, we
just...
can hear you okay.
Okay,
Yeah.
excellent. All right. Okay. So again, good morning, everyone. So my name is Sean Horgan. We welcome to this latest in the series of webinars that Smarix host. I trying to give everyone a chance to log in. So just sort of not rushing straight in because I think there's lots of people due to attend today. So well, I will start go through this sort of the who else is actually assisting here today and presenting to everyone. As I said, my name's Sean Horgan. I head up the sales activity here. I've got some colleagues of mine, Michael Clapp from Smarix UK, who's our technical director. We've got Dr. Vignesh and Shrant are here from our Smarix Detroit office. We've got a packed agenda, so we're going to sort of try and get through everything, within the hour, as sort of stated. Yeah, some people on the call probably do know me already. I joined Smarix a couple of years ago, actually. But I've actually been working with Smarix for sort of over 15 years because we were their UK distributor for a long time. We decided to merge our business with Smarix and form Smarix Limited. So it's the fifth Smarix office that exists globally now. And it's great. So it's my pleasure to sort of be here and sort of try and help continue the growth of Smarix across the world. What we're going to do, there's the agenda we have we put together here. Within that sort of 60-minute commitment. I do appreciate everyone's time this morning. So what I want to do is, first of all, is just go through a little bit of an introduction to Smarix for those of you who don't know us, and also sort of why so many turbo machinery companies are turning to our software. We're then going to show the software in action and try and sort of Mike's going to do a demonstration of Smarix working with CF Turbo, a turbo machinery design tool, one of our partner companies. And then Vignesh is going to go through some of the more recent optimization technology that we've brought out that clients are already making use of. And Shrant is then going to take us through some sort of final case study material of other sort of various turbo machinery applications. So that's our plan. Yes, there'll be plenty of opportunity. Please, if you've got questions, post them. That's fine. We may not be able to get to them today, but we'll certainly, follow up and come back with any questions that you might have during the event. So yeah. So that's our plan. Yeah, I think we'll crack on if that's okay. Yeah. So first of all, again, for those people who don't know us, say welcome to the world of Smarix. The company been around for getting on for 20 years now. Actually, when the company was formed, the founders very much had a mission plan, if you like. They very much wanted to solve CFD applications that typically the other CFD vendors that were around really weren't doing that great a job of doing. And that was particularly where you had, moving machinery type applications where there was some sort of dynamics in the system, whether it be a displacement pump or a centrifugal machine, but basically wherever there was something moving, that's really where we Smarix felt they had some ideas, some processes that we could really add value to all those sort of existing CFD users that are out there. It was proved a success. So we're now 65 people around the world and growing. Our mission hasn't changed. We still want to provide and still do provide fast, robust, and accurate CFD solutions. And automation is at the heart of what we do. That's always been at the heart of what we do, and it will continue to be at the heart of what we do. So yeah. In the early years, we focused on talking to clients that we knew were struggling with modelling those harder problems, and whether it be the automotive industry, powertrain type applications, there were a whole series of clients that we basically could do things much faster, much more efficient, and we proved it on all these sorts of all these sort of case studies, all these client examples I'm showing now. So so it was something, basically it was very much wasn't really a a sales strategy. It was very much we've got some technology that we think is different and it works, and it is so much faster than what they were used to doing. As a result of that, all of these companies have became early users. And over that same period of time, from them until now, we now also have hundreds of sort of turbo machinery type applications at companies as well. So I mean, I think there's in the centrifugal axial pump world alone, we've got over 100 sites, and these are just a few of those companies. And again, it's what this webinar is about today is trying to illustrate to everyone who's on the call sort of why these companies choosing Cimerix over other CFD, because often a lot of our clients have already got CFD, so they bring Cimerix in to assist or because it can do things so much faster. I mean, more recently, we've seen an upturn from other turbo machinery type applications, so fan companies, compressors, turbines, propellers, and turbochargers, these sorts of things. So they it's as we grow as a company, as we get to talk to more people, the fundamental core part of our technology being fast, robust, accurate, it really resonates with a lot of people, and yeah, we're just very happy just to have so many more people sort of turning to Cimerix, as opposed to we continuing to use other solutions that they have. So what is it about Cimerix? Well, yes, in generic terms, this is what we're trying to do. We're trying to help people be more efficient in the way they use CFD, whilst maintaining the sort of the performance accuracy that they need to when they're doing simulation, if you're going to use simulation at all. How do we do that? Well, all of our technology is our own. It's been developed by the founders, by the people, our founders that started the company. They're still very much part of the company. They still do the development work, and the team is strong there in Seattle. But very much always, every day, we're always thinking about how can we make the solver faster, how can we make the meshing process easier, and so speed is always important to us in everyday sort of development decisions. Also, allowing people to mesh efficiently, robustly, so that you're not having to spend days worrying about getting a good quality mesh. Cimerix does that for you. And that's really, again, what we try and ensure. But all the time, though, we know that our clients aren't going to be using our software unless we can make sure that we provide accurate solutions too. So that's, again, there's no compromise in what we're doing here. We obviously want efficiency, we want more speed, but at the same time, we want our answers to be as accurate as they can be. We've enhanced the setup process from the very beginning. We have a template philosophy, so depending on the sort of the machinery type you have, you can basically grab a template from our library, and it then steps you through the process of building a mesh and setting up the sort of the operating environment, the conditions, etc., that you might need for that particular type of machine. So that again is an area which helps speed up the whole process. In more recent years, again, we've been partnering with a lot of other companies, and we now have embedded sort of CAD front ends for various systems. So there's things like Creo and Rhino and X Fusion. We can put Cimerix right inside your CAD system if you want. At the same time, we have various technologies and processes for integrating. So really, irrespective of what design solution you're using, Cimerix now has a way of becoming part of that design process. And that really leads to sort of leveraging your CAD geometry, because ultimately, that's what a simulation tool should do. It should be making use of your 3D CAD systems. Part of CFD, the first step is always to create a flow volume. You have to have that empty space that exists, needs to become a part, so we can do some analysis on it. We do that. We can do that inside the CAD. We can do it outside the CAD, your CAD system with our new Cimerix CAD that's coming out. And we've also got beyond CFD. So a lot of our clients are saying, well, what about optimization? What about acoustics, radiation, electromagnetics, FEA? Can you do these other things? So again, during more recent years, we've added to our portfolio, and now you can do a lot of these things inside the Cimerix GUI. Customer development. A lot of our customers do want, often ask us for something very special, and typically the answer is yes, we can do that because we've got this very powerful expression language that comes with software. And the last point, I think a lot of clients recognize is because we are still independent and intend to remain so. Again, the founders are very much that's the mission. We want to provide a choice to people out there. So many CFD companies have been bought by CAD systems, bought by CAD companies or other big electronics companies or whatever. But we haven't, we won't be. We're CAD neutral, and that really is something that we wanted to provide a choice, an option, for our clients out there. So diving into a bit more to sort of the why Cimerix for Turbo Machinery. I mean, basically, these hundreds of clients that got out there doing work with Cimerix every day, they're typically doing a number of different things. So what's primary importance most times is what is the performance of my product? Sort of, it's a given. Whether it's they're looking at it at a component level or looking at how it performs in the system, that's clearly what they want to know. They want to be able to virtually test that. At the same time, when you're making design decisions, you want to compare very quickly. So you want to have a means of doing prototyping, but doing it virtually. But drilling down further, there's things like what's the impact of cavitation might have on the system of this pump? Is that going to cause failures? Are there noise issues occurring or pressure ripples? Analyzing loads, leakages, MPSH studies even for a pump. These are the sort of things that our clients are doing every day. We're used to supporting them. We have experience of these types of things. So again, that drives us in terms of how we're developing our software and how we're looking after our clients. On the issue of performance, everyone asks, how accurate is Cimerix when it's so fast? Well, very accurate. It's this is a test done many years ago by Flowserve, but you sort of see here we have two approaches. We have the steady state, sort of quick, very quick analysis where you can tend to pick up trends and make design decisions, but if you really want to nail the numbers, the experimental data typically we're always advised doing transient calculations. And if you do that, then this is what we would typically expect when we're doing these comparisons experimentally. And this was another client, did an evaluation. They had an existing CFD tool. They had 3 test cases they ran, and they produced all this data, which, and again, all about how close we are to experiment. But the important thing about this one is just what they quoted when they wrote the report up for this, was that it was really that, yes, it produced very accurate answers, but it was the speed at which Cimerix could do that. I mean, they were spending less than an hour typically on preparing their CAD models. It would just mesh straight away for them. The whole process was 10, even 30 times faster than what they were with their existing CFD tool, and their accuracy levels were within 1% and 3%. So again, once clients typically do these tests, the argument for Cimerix becomes pretty compelling. And it's not just sort of where there's some sort of motor driving the system. We also can do fluid-driven activities. This is a torque motor example. Again, you sort of see how accurate we can be. So there's lots of capabilities in the sort of turbo machinery area that we have. Last few comments I want to make about sort of testing as well. How we're testing, it's obviously critical. Everyone's always going to carry on doing that. And we really what we're trying to do is help people optimize the amount of physical testing they're doing. It's not necessarily replacing it; it's trying to optimize it, because it can be a lot of trouble building these test rigs, and such as here where you look at putting a special test rig where you can actually see inside what's going on. Every time we do a simulation, we're always seeing what's going on inside the product. So we want to make the best use of the physical testing you're going to do, and that's what Cimerix is all about. The way we present the software to our users, we want people to get the information out quickly, efficiently. So whether it's pressures and velocities, temperatures, cavitation quantities, torque loads, torques, these things we want people to be readily available. And the only way you can do that is if you've got a tool that is fast, robust, and accurate, that's doing these things quickly, efficiently, reliably. So that you end up with this type of solution. Okay. So in summary, we've got yeah, it's all about speed, without you know any compromise on accuracy. If you've got small features, we'll include them because sometimes they can be important. We've got a range of physics modules that address all sorts of different things, such as cavitation, etc. The robustness, getting a complete performance curve across the turbo machinery device is always very important. So we're very confident about that. And also, if you need to do full-blown system simulations again, Cimerix has that capabilities, and it does it, we believe, a lot better than anyone else. And yeah, less than 2 days training is typically what we ask for people to when they want to start using Cimerix if they haven't used it before. So the last thing I'll say is just this sort of set the scene for the sort of demonstration you're going to see. Again, we feel we have lots of different solutions for the way Cimerix can fit into your design process. What we're going to show you is actually how we can very, very, very quickly, very efficiently go from CF Turbo, turbo machinery line, tool straight into looking at virtual test results. So, and that's really what what's about. And then we're going to go on and talk about how we go about optimizing things and et cetera, et cetera. So that's what's coming next. So I'm going to just stop sharing for a moment, and I'm going to hand this over to Mike. Yeah, that's okay. So Mike, can I make you the presenter?
Okay.
There you go. You've got it. You've got the thing. That's it. We got you.
So, okay. So what I'll do here is actually go through the whole process in CF Turbo. So sort of let's start by designing a pump in CF Turbo. So if I click on the pump generation thing, I can actually just give it the design point that I wanted, the best efficiency point I'm designing for here, and click OK on that, and it will type give you an indication of what type of device that's coming up with. So it's a radial impeller there. So if I click OK on that, CF Turbo will basically step you through the process here. So the first thing to do is create the impeller, and I can go through various setup things here in terms of what type of, whether I want it shrouded, unshrouded, or whatever, and put in some basic dimensions. Or I can actually just hit a fast forward button here, and it will just immediately generate a pump impeller for me. So on top of the impeller, to do a CFD analysis, I also need a volute on the outside of this. And again, there's a process you can step through designing each of the stages of the thing, or I can hit a fast forward button and it will actually create that. And as far as the CFD simulation, I probably need an extension in the outlet of the volute, so I'll add that in. And it will also help to have a tube on the inlet of the impeller. So I'll add one of those in here. So let's just lengthen that slightly. And there we are with a 3D model of a centrifugal pump ready to do. So the question then comes is that going to give the performance I need? So just one thing to set up in terms of getting it ready for the CFD is just to add a connection between the impeller and volute. Click OK on that, and we can come to project here, and we could export that to Cimerix. First off, though, I'll just actually save this model. And if I come to export here, I can just select all the components, make sure it's a virtual domain, make sure we're using a relevant version. Plus, and then we can just hit export here. There are a lot of controls in here as well for setting up the refinement level of the geometry the STL mesh is going to come up with, and then the finite volume mesh is going to come up with. Well, in this case, I'll just leave it to default. So basically, it then goes away and creates the STL files of those four components on the thing, fires up Cimerix and checks by license and carries on from there. As it's taking a bit of time to generate the mesh, rather than keeping you waiting, I actually just have that process completed here. So you know, this is the mesh it will come up with on there, and you can actually, so there it's just started to do that meshing process. So I could actually just show the grid it's produced and so on. And then I can actually, this model is just totally ready to run. So I can just hit the start button on this. And if I show the pressures on here, you can actually start seeing the pressures develop as the solution progresses on there. So yeah, and it's so that's actually finished the mesh on the other one now. So that gives you an indication of the time involved on that. So that's the pressures. I can also look internally on here, so I can get streamlines out, and I could actually color those streamlines. Right. Okay, so I got that back again. So you can show the velocity colored on there, and actually I can animate those as well. So on top of that, I also showed sections through the thing. CF Turbo will actually automatically find those sections for me, so I could actually put show velocity on those, so you can get an idea of velocity flow patterns. And if I add vectors to that, I can or show the colors on those vectors, and you can start diving in and seeing where things are. So you probably also want to get out from here sort of some actual quantities. So basically at the bottom here, we've actually got a great graph going already showing the overall head that the pump is generating. So you know, if I zoom into that, the design was 50 meters, and I've actually just got a little overlap from the design, so it's performing well there. And you can get efficiency graphs out of here, so get up to about 78% efficient there. And you can add more graphs in here, more information. So for instance, I could get the power out of this here, and you can actually, you maybe want to change the units of that. So you know, it's about 20 kilowatts is required to turn the pump around on there. So if I that, you can see that I am doing that. So it has now 500 iterations of the steady state simulation. I could also actually just restart this simulation as a transient simulations, so 60 steps with a revolution, and just it's as simple as just starting that again. So the transient simulation will actually capture the interaction between the blades and the cutwater, which actually tends to increase the accuracy of the solution. See the animation coming on. There are also sort of other plot information I can get on here. I can get a cascade plot of this. So if I show the velocity on there, maybe I can show the vectors, and I could show the relative velocity, velocity magnitude. So this is a section halfway through the between the shroud and the hub, and we're showing how the flow patterns develop through there. To actually illustrate that, I could, or where that is, I can actually just change this to a 3D mode, refresh it, and it then appears in the real position. So you can sort of slide this up and down and so on. So basically that's in the last sort of 5 or 10 minutes, I designed a pump and simulated it fully steady state and started a transient calculation on this. So we are well on the way to sort of design that. So really the next step from there is to talk about optimization. So I can hand over to Vignesh, who will explain some of our optimization capabilities.
Thanks.
You ready?
Yes.
Vignesh?
Can you enable the sharing, please?
I can do that for you. Here we go. You've now got it. You should have it now, Vignesh.
Yes. Thank
Okay, excellent. Thanks, Mike. Brilliant.
So I do have a small demonstration of our optimizer. So before going, I would like to going over the demo process. I would like to go over a presentation so I can explain how our optimizer works. So in general, we have broadly we categorize optimization into 3 methods, like gradient based, adjoint, and probability based. And what we use in Symantec is Bayesian optimization framework, which falls under probability based technique. So the good thing about Bayesian framework is it's widely used in machine learning, and it's a black box function in the sense like you don't need the optimizer itself doesn't need to know about CFD to perform the optimization process. And also it needs fewer model evaluations compared to other optimization techniques such as gradient based. So that way we don't have to do much CFD. We can get away with doing fewer CFD optimization runs and getting the optimized solution. So this slide will show how this Bayesian optimization works. Say if we have one independent variable x and a dependent variable f of x, and we say this blue line is the relationship between these two, right? So I need to find a point x where this f of x is the maximum. So that's my goal. But say I don't know this blue line yet. In a real world CFD simulation, you don't know the relation between the dependent and the independent variable. So you have to start somewhere, right? So then for this simple case, we can start with 2 DOE runs. So the easiest way to connect these 2 points is through a line. So that's what we do. And also we calculate something called like probability of finding the maximum point. So here, like we can clearly see the probability of finding the maximum point is somewhere over here. So that we use some calculations to find the probability. So now we have two things, right? We have this black line, which is the actual line that connects these 2 points, and also the probability. So we collapse it into one function called utility function, and basically giving weightage to both the probability and then the black line, the maxima pointed out by the black line. So then we get the utility function. The maxima of the utility function is where our next design we need to evaluate, right? So then we march forward, and then we evaluate that point, and then so then we can connect it into some sort of a polynomial, right? And after that, what happens is, like, you see the maxima, the black line pointing out is here, but our probability is pointing out here. So our utility function, when you take the mean of both, so what happens is utility function is pointing here. So that's the basic concept of Bayesian optimization. It's not going to just go wherever the the polynomial is fitting and showing as a maxima. It also goes by the probability of finding that maxima. So this is the design point, next design point. And then we evaluate that point, and we know it lies on the blue curve. So we plot that in this graph, and then we connect it again. And then now see the probability has happened in maximum here, and then the black line is also pointing somewhere there. So utility function is pointing it there. So then we do this. So all this is done internally inside Symmerex. I'm just showing how this process is done inside, just to give a general idea. So within like 7 or 8, we are almost like 6 or 7, we are almost close to the peak. And so we almost reached the peak here. We almost found the peak here to local maxima here and here. So that's another thing about Bayesian optimization. It doesn't just stop after finding one peak. It also tries and goes. To explore other locations because the probability map. So that's what makes it possible. Like looking at both the spline, the polynomial that connects these points, and then the probability makes our optimization more robust, and it's able to explore pretty much the whole parameter space, and we are able to get the whole curve, pretty much the whole curve, and then the local maximas within like a few iterations. So that's how the Bayesian optimization in general works, and that's how it works inside our software. So also to begin with, we started with 2 DOE points, correct, for a simple case like the previous one. But in reality, we have many independent variables, like blade. Say like in a pump, you will have like 6 blade angles, let's say. So then you have to distribute the sampling points evenly in the parameter space. In this case, say there are 2 independent variables, X and Y, right? So if you are like distributing it randomly, you might leave some parts out. You might not be exploring certain parameter space. So that's why we use this technique called Latin hypercube sampling, where you put effort to distribute these DOE points evenly in space. So this is a 2 parameter space. Be 10 parameter space, you will still be able to distribute it evenly. So this is the default option in Symmerex, but we do supply random sampling in case the customer needs it. And this is the module interaction. So we like, I hope everybody has heard about Symmerex and the CFD software. It's been there for like 20 years, and this optimization tool is relatively new. It's like, say, like 5 years, give or take, but now it's really mature. So, and it's tightly integrated with the CFD solver. You don't need to go to a separate window to access the optimization tool. And so now we have the optimization tool, the Bayesian optimization, which I explained, and then we have the CFD solver, which Mike explained. But the missing part was this design software. That can be anything like Creo, SolidWorks. In this case, for today, we are using CF Turbo. We are going to talk about CF Turbo. But the idea is we need to change the surfaces by some means, correct? That's the whole like point that needs to be done. Like you just need to change the surface to do the design. So that can be done in many software, and we are choosing CF Turbo because they have all these sophisticated design options for centrifugal equipment. And yeah, so this is where it fits. So it's so these two are tightly integrated, and this we are using different software to accomplish the parametric geometric tool. So then this is a workflow of CF Turbo itself, the optimization with CF Turbo itself with it's pretty similar to other CAD tools too, but this is with CF Turbo. So you start by what Mike did, just create the CFD simulation. Within like 10 minutes, you can do that. And then you create a sampling plan, like how many DOE runs do you need? And how many optimization runs you need. Those things you need to pick. And then we start with the DOE loop. So you start from the sampling plan. So say you have the DOE points distributed in space evenly, and then you take one point and create a new design using CF Turbo. And then you conduct the CFD simulation, and then you construct the surrogate model. And then say if we are doing like 50 DOE runs, like you do it 50 times, and then you refine the surrogate model each time, basically this loop. So and after 50 times, say if you want to run another 50 more optimization run, then you enter this loop, optimization loop, where you check from the surrogate model, which is the next, like, best point. And then we pick that best point, like that could be the possibility of that being the best point from the utility function, like I showed. And then you take the new design and then conduct the CFD simulation and refine the surrogate model again. Like you haven't stopped refining the surrogate model after the DOE run. Even during the optimization run, you keep refining the surrogate model. So your prediction gets better and better each design change. So and then you do it until you are done with until you exhaust the optimization run. So that's the basic workflow. And just to show like an example, I would like to show this multi-stage pump, which we did for one of our customers, and it's been published in the journal. So we have this multi-stage pump, as we see here, and then we have 21 parameters, and 11 of them are key parameters, which needs optimization, including blade angles and number of blades and many other constraints. And what our goal is to maximize the efficiency, maximize the head with strict design constraints like the impeller diameter and things like that. So, and then this is the optimization process, DOE runs and optimization runs. We did 50 DOE runs and then 110 optimization runs. Clearly see, as you can clearly see in the DOE runs, there is no real pattern. We have the efficiencies all over the place. But once optimization runs, like our optimizer tries to find the best design for each design variable, and then it tries to optimize the single stage efficiency. And we can also do sensitivity analysis with the DOE runs, because DOE runs is it's randomly distributed. In our case, it's Latin hypercube based sampling, but still there is no specific pattern on how we distribute the parameters in the design space, right? The DOE points. So so that's a very good case to do a sensitivity analysis, because there is no bias in this data. So that helps you find out which parameters have more impact on your outcome. Like, so for example, COLI hub has a major impact on the head in this case. So then this parameter needs a closer inspection, but the ones that don't have much effect on the head, we can ignore them for the next optimization run. So we usually start with many variables, and then we do this single run of optimization, then we drop many of them actually, and then just only keep whatever that has a major impact. So that's what Pearson sensitivity does. Like Pearson sensitivity points out which variable have more impact on the objective function, in this case head. So this is the base flow, and here you can clearly see some recirculation happening over here. This is the cascade view which Mike showed earlier. So this is probably the problem in our design. We need to probably get it out there. So we set up the optimization, and then we were able to get this optimized design where we were able to completely get rid of this recirculation. And this, we didn't have to even realize there is a recirculation. We didn't have to change the blade ourselves manually, right? It automatically does it for you. So that's that's very powerful. Like you can change something, some physical aspect of a fluid without really realizing that that's the cause of the problem. So it's you don't have to really think about that so much. So that's the key point to show here. And then we're able to improve the head and the efficiency by 24 and 18% respectively. So and this is how our optimization process looks like when it's trying to optimize, when it tries to talk to CF Turbo and optimize the design. This is how the optimization process looks like. And here are some of the pressure, head, and efficiency comparison. And solid lines are baseline and optimized design, and the dotted lines are just the experiments for the baseline. So we clearly see some improvement in both head and efficiency areas over different flow rates. So yeah, so that's the presentation I prepared. I hope it's clear that how the Bayesian optimization works and how it's integrated in our software and how it's talking to CF Turbo and whatnot. So now I will start the demo. It'll take like 5 minutes to show. So like I'm going to start where Mike started. So you just need a CF Turbo design file. In his case, Mike prepared the design himself. I'm just going to use the tutorial case which we have. Right. So and then so what you do is you go here and then a project, and then before that you can do the 3D view if you want. So this is how the pump will look like. Right. So and then you go here and then go to export. First, get the project files, Symmetrix project files. You select all of them and then select export all files, and then say export. Make sure you select Symmetrix over there, and then click export. Okay, so it took like 8 seconds. Okay, here's we started with the design file. We got a bunch of files, like of which one of which is the Symmetrix project file, which you can open to just simulate just this design. But that's not what we're interested in now. We want to set up the optimization, right? So then we close this, and then you go to the batch mode or optimization. Here they give you a chance to pick whichever the variables that needs optimization. Like for example, like these blade angles, I'm going to select these 4 blade angles and then 2 more blade angles here. I'm going to optimize for 6 blade angles, and then here I go in the export option. I select Symmetrix, and then I select this, and then make sure the make sure only exporting STL files only, because we don't need to export the project file now. Every design change, all we need is this impeller. Basically, we don't even need these. Just the impeller is what it's going to change, right? Because the blade angles are associated only to with the impeller. So so only STL files concerning that, and then click add, and then you click save. Just save under the same name, tutorial. And then that's it. So if you go back to your folder, how it will look like, you will have an additional file called batch file. So this batch file acts as an interface between the design file and your Symmetrix project file. So this is how you communicate between these 2 files, actually, the design file and then S profile in case you're wondering. So that's yeah, so I'm just going to close this, and yeah, so that's the part with CFTurbo. Now we have to do some more things in the Symmetrics part. Now we got the batch, we got the S profile, so but we still need to add the optimization module. So I already added it in this project. I opened it and I added it. I can go over how I did that. So you go to the this is our S profile is a Symmetrics project file, and then you go here, and then under the models you can select optimization and you can add it here. So I already added it here. So and then under the optimization module, so like you will see some of the options which I mentioned before. So this Latin hypercube, you have the option of selecting random or Latin hypercube, but I'll leave it at the default, which is the Latin hypercube, and I can make it extended mode to show there are any more options. And you need to select all the. I remember I did 6 blade angles, right? So you need to declare these 6 blade angles here, and then you need to give the min and max of those 6 blade angles range. And then we need to pick up the objective function. In this case, I'm doing efficiency, and then I'm doing a steady state simulation. The last 50 values of a steady state simulation, I'll calculate the efficiency, and that will be my objective function. And I do this for every design change. And then you can add constraints if you want. Say like I want to maintain at least certain meter of head. You can give head as a constraint too here. And yeah, and then this is the external parameter. So this is we link these parameters, basically the internal parameters with the range. We need to link it to the external parameter. This is the external parameter is the CFTurbo parameter. So we need to link this internal 6 blade angles, which are optimizable, try to optimize, to the external CFTurbo. So that is done basically here in this section 1 to 6. It's basically like how many ever variable you have, you create that many variable here for linking with external parameter, and you need to tell which CAD surfaces that need changing. In this case, all the impeller surfaces that needs changing. So so you need to create like that many geometry update. So that way during each design change, these CAD surfaces get updated, and that's pretty much it. Very straightforward. And these are some advanced options if you're interested in exploring more about the Bayesian optimization. We just suggest them to leave it at default. You can also change with the explorative coefficient, which controls how this optimization process is usually done. But this is, we don't need to usually worry about it. We can get 99% of the time we can get away with the default Bayesian optimization settings. So yeah, that's how we set it up, and I can quickly show the run. I'm going to start from initial values. So I'm also going to show you this command prompt, which actually this is how we talk to CFTurbo. This command prompt, like if we launch a new command prompt like this, and then inside that we're talking to CFTurbo and getting the design. So what CFTurbo has done is CFTurbo has already generated a new design now. It's and then now it's being exported. It's been exported, and you will quickly see that this blade design will change on the screen. See, it's changing now. So yeah, so it's so this is our first design, and you should be able to see some results soon. See pressure, you're able to see the pressure, and Mike has already showed all the post-processing capabilities. So I'll just leave it at that. So, but the idea is we were able to change the design using CFTurbo with a very minimum like work, right? And then there will be a second design change incoming. So first, I just put 30 iterations so that I can show the design change. But yeah, I will have to run a bit longer. Say I put only 30 iterations. But yeah, so.
Okay, Vignesh, that's great. Conscious of the time, so that's brilliant. Thank you.
Yeah.
You there yet? You sort of, yeah, good time to hand over?
I'm done. Yeah, I'm done.
Okay, all right. Okay, all right. Yes, Sharant, are you available?
Yeah, can somebody give me the presenter?
Yeah, there we go. You've got the presenter. Thanks, Vignesh.
Yeah, hi all. Hope you can see my screen. Let me make it into a presenter mode. So I thought I'll go through some of the case studies that we have done in the past to show some of the capabilities that we just talked about. So the first one is about the cavitation modeling. For turbo machinery, cavitation modeling is something that is fundamental, and we have had this cavitation model for a very long time. So as I think a brief understanding of cavitation, probably everybody here is aware of it, but it's just the formation of the vapor phase of a liquid, right? When the local pressure goes below the saturation pressure. So the vapor bubble will grow and it travels to this travels in this low pressure zone. So when these bubbles collapse due to this high pressure, and you can generate like a shock wave in terms of the high jet force, and this is the reason for some damages that it causes on the surface of the material. So numerically, this is quite a stiff problem to model because as the bubble grows, essentially the pressure from the outside needs to kind of be tightly coupled with the bubble growth formation. So, and it's essentially the rate of the growth of the bubble is dependent on the pressure and vice versa. So you have to tightly couple this problem, and usually the solvers kind of struggle on this. I think if you look at other solvers in the industry compared to Cimerix, this is something that we do in a bread and butter case, and we do it in a very robust way. So the density differences typically can be in the order of 10,000 or above, and since the ratios can be this high, any small changes in the cavitation region gets very amplified in the cavitation region. So that's part of the reason why sometimes some of the other solvers struggle with the convergence, basically. In Cimerix, we have 5 different levels for a cavitation model. We start with a basic model, constant gas, which is addressing free air and liquid as well as the vapor of the liquid. And then we have all the way to the highest complexity where we have the free air, dissolved air, we have the vapor as well as the liquid. In this model, we also have rate constants that dictate how the air, expands and collapses. So it's a very sophisticated model that can be used based on the need for the physics to be modeled. So here I'm showing an example of a vane pump. Essentially, as everybody realizes, the flow rate curve of the vane pump is directly proportional to the speed. So here's the flow rate in the y-axis and then the speed in the x-axis. And you can see that it should be a linear curve. But when cavitation occurs, what happens is the curve kind of deviates from the linearity, and at some point you will see that it sharply plateaus. And that's the experimental data here in the dotted points. And you can see the Cimerix simulation can capture this trend quite well. And that shows that the cavitation model that we have implemented here can pick up the fall off of this curve as a function of the speed of the pump. And here on the picture on the right, it shows the amount of vapor or air bubble that gets formed, basically. The next test case is of axial flow pump. Essentially, this pump you have in a test chamber, and then you have pushing some flow through it. And when you're running it at certain speeds, you will see that a cavitation bubble kind of pops up at the blades, right? So we can essentially study this bubble as a function of the flow rate that you're pushing. And this is what has been done with the test data, and they kind of monitor the bubble that is getting formed on the blades as a function of the flow rate that is coming in. And what you can observe here is the simulation results on the left side compared with the experimental data on the right side for the different flow rates that we have run. And as you see, as the flow rate increases, the bubble size kind of drops. And at some point, we can see that the bubble kind of becomes very small. And that can be captured by the simulation quite accurately. Here I'm showing qualitative pictures, and we also have quantitative numbers in the paper. So the next point is about the NPSHR. So for any tool that does turbo machinery, NPSHR is something that is needed for you to have a tool that you can help in designing of this pump. NPSHR is nothing but characterizing let's say in this equation, you can see the total pressure and the vapor pressure of the fluid. And when the pump operates at 3% loss of the head due to cavitation, that's where this NPSHR is, that number is calculated. So CFD actually offers the glimpse into the operation limits. For that, you need to have a good cavitation model. That is the foundation of this NPSHR. You need to have a cavitation model that can capture the physics accurately so that you know that this is the NPSHR of the pump. For this, what we have done is we have developed an automated tool. Essentially, the tool kind of guides the user through the process of calculating NPSHR. We have like a paper that lists the different steps that you need to follow, and we have used that paper that we have written to create this automated tool. So it becomes a automatic process for the user to just go through this to calculate the NPSHR for any centrifugal pump. Here I show a demo case where so the pump was tested in the test rig, and we have a fluid model built in Cimerix. One thing we can observe is we capture all the leakage gaps. We have a structured template mesh that can be coupled with the outside mesh using our mismatched grid interface algorithm, which will then capture the flow leakages quite accurately. And then I'm showing the mesh cross-sectional view here. So first left plot shows the performance, the total head as a function of the flow rate. You can see the favorable comparisons of this with Cimerix data for the CFD transient. MRF is also an approach that we use to get quick results, but it can be a little bit off from the test data because it does have an assumption of a fixed blade, and then it's just using the reference frame approach. But using the transient run, we can do the NPSHR study. This is on the plot on the right, we're showing a head drop at a certain flow rate as a function of the NPSHR. You can see that the curve here is the test data, and we can capture the Cimerix data captures the drop quite well. So we can essentially see that there is a sensitivity to the percentage of air that you use, and can capture the drop as at 8% of air. And using that 8% air, you can run the other points or the other flow rates, and you can see that we can capture the test data quite accurately. And this is the paper that has been published at this conference at ASME. The next capability that we have developed in the turbomachinery field is the acoustic capability. This is it's been there now for a year or so. It's fully parallelized. You can do moving sliding meshes, and it's inside Cimerix interface. It's our own native acoustic solver. So you can just pop in this module in your Cimerix simulation, and then we have 3 different models. So we have the source only models, which is the broadband source and the Lytle stress. And we have a source transmission model, which is the Fox-Williams-Hawkins FWH model. To validate this, we have done quite an extensive amount of study, but here I show a fan study that we are publishing now at a conference. So this is the EA experimental setup. So you have this fan in an anechoic test chamber, and they're measuring the noise at different probe locations, right? And this is done the experiment, and then we run the simulation in Cimerix. So of course we have to do some refinement around the fan to capture the eddies that developed coming out of the fan, and then we also have to use the LES to get favorable comparisons, right? So this is about 28 million cells. We can run RANs as well, but the LES compares more favorably typically for these type of applications. So first we look at the performance. This is the delta P, the total pressure rise as a function of the flow rate. You can see the comparisons between, let's say, Cimerix LES with the test data in the black dots. And we also compare the pressure side and the suction side actual velocities as a function of the radial location that we compare that to the test data. And then finally, we look at the acoustic noise level. Please note that we have a script that automatically actually can do this processing and give you a plot of this PSD as a function of frequency. And also we have a script that also does the noise actually as you hear it. We translate this to the noise that you hear in case you want to kind of hear it physically, right? So the thing that is noticeable here is how we capture the peaks. The location of the peak capture is pretty exact, and also we see our data kind of lies within the band that the test data measurement has. For the probe 1, you can see we are a little bit higher on the high frequency. The reason is potentially the hub of the fan actually probably blocks some of the noise, but we don't have the solid noise propagation in our model. It's all fluid noise. So we don't see that attenuation at high frequencies in our results. One thing to note is other tools at other microphone locations, they struggle to capture the high frequencies. You can see that one of the tools, they don't even have the high frequency after 5,000, whereas the test goes all the way up to 10 to the 4. So, and also, the way we run this, the speed at which we run this is significantly faster than what some other tools can do. One more case study for the acoustic that we have published is for a design of the Girotor pump. They have two different groove designs. D1, you can see the groove looks like this, and then D2, the groove looks like this. And what they have done is in the test is they have kind of measured the frequencies, the SPL levels, normalized as a function of frequencies, right? And what they have observed is at D1, the design one, they see higher noise levels compared to D2. And this is something we can capture. You can see here in our Symerics results on the right, you can see the higher red spots compared to D2, lower red spots, and the same with the lower frequencies as well. This is something that we have published. This is one quantitative data. The paper has some more things, so I don't have all the time here to go through it, but if you're interested, we can share this technical paper with you. The last one is the FEA capability. This is something, again, we have developed from scratch. It's our native FEA solver. Now we have used it in a few cases, and this is a screw compressor case that we use the capability. So essentially for twin screw compressor, due to gas temperatures rising during the compression process, it can cause higher thermal expansion of the compressor. So this can change the leakage gap, which can be very important because you're pushing air through, and leakages can affect the results quite dramatically. So the way that works now is we have Symerics CFD solver, which is the fluid and the heat transfer model, and that talks to the Symerics CFD solid model, which solves the heat transfer. And this loop keeps performing till we have some flux convergence, and then we go to the structural solver to modify the geometry, and then come back and then do the coupling again. So this is what is explained in this algorithm. So the fluid mesh is about 3 million, the solid mesh is about 0.4 million, and you can see we can model the gaps using our general gear template. It can be essentially, ours is a very unique approach. We brute mesh the entire thing and we squeeze it into a very small gap, all the cells, and still the solver can handle the mesh without any convergence issues, right? This is a pressure contour and a temperature contour. There is no necessity to babysit this process. You will be guaranteed a solution, and you're not going to diverge. This is something that we have done quite a lot of cases with this general gear template, and it's extremely robust. And here you're looking at the solid temperatures and then the rotothermal expansion that is plotted. So once the thermal expansion distribution comes in, we go morph the geometry of the solids as well as the fluid, and then we come back, and this is an automated process that is written using a script, basically. And the resultant of this is essentially the mass flow rate from the simulation, and then we compare that with experimental data as well as the rotor power, and we get favorable results, right? Just to conclude, I think what we have done now in this field is we start with the cavitation physics, which kind of dictates the NPSHR for any pump designing. We have added the acoustics, we have added now the FEA, and now we are coming up with our own CAD kernel. We call it SMP CAD. And that's going to make it a product portfolio which addresses multiple physics, which does it in one platform, and we do it in a robust, fast, and accurate way, which other people can claim, but we have a product that does it. So I'll end it here. Hand it over to Sean. Thank you.
Okay. All right. Thank you. I just want to sort of put my camera on so you could all see me. I'm just going to sort of finish up here to sort of just last couple of minutes here. We had a sort of a lot of questions coming up, which there's really just no time to address all the questions we had, and a lot of them were very, very specific, and we've made a note of them all. And what we'll do is we'll make a point of coming back to you on a sort of individual basis. Some of them were very specific to various optimization things, everything. So I think today we wanted just to I could try and cover some of the questions that have come up in the last few slides I've got, but I think it's we'll just have to come back to that because I'm conscious of everyone's time. So the last few things I wanted to sort of say today. Basically, we as a company we are around for quite some time now, and our client base, we tend to look after them very well, and our clients know us, and that's great, particularly in the fluid machinery space. The thing is, in the sort of the bigger marketplace, the world, Cimerix still isn't known as well as other CFD tools, and that's very much what we were trying to do and make different, if you like. So because the CFD usage is going to continue to expand, fluid flow, heat transfer, it's all around us, and so basically we've traditionally. We have a lot of clients who are full-time CFD analysts, and that's great. And we've also got a lot of people that are, the design side of things that do a lot of work with Cimerix through our partner companies as well. So, but our vision, if you like, the way we want to be different is to be able to very much sort of fill this sort of void that exists, because there's lots of very sort of challenging engineering problems out there that involve fluid flow, and you need the fidelity of a CFD tool that can give you accurate answers, has all the sort of physics that can run. It needs to be robust, but at the same time, it needs to be efficient. It needs to run quickly. It needs to fit into your design process, and that's really where we feel Cimerix is different, in that it can provide all of these things under one roof. A lot of people our clients sort of know about us, and that's fine. But what a lot of people don't actually know is that a lot of other software companies have started using Cimerix as part of their solutions. And, there's a company called Orca 3D in the marine sector, and PTC themselves, CF Turbo, etc. They provide Cimerix to their clients as part of their offerings, Rhino, etc. So SimScale. So these people have probably heard of these other companies, but what people don't necessarily know is that the CFD they're using is actually from us, and so that's enabled us to sort of go forward and develop a whole range of capability to irrespective of what CAD system you're using, irrespective of how you're driving your CFD. We've tend to got ways of we have solutions for doing that, and one of the things that's culminated is that very shortly we've got a new module coming out called Cimerix CAD, and that's very much our ability to just bring in any format of CAD directly into the Cimerix environment, and do extract your flow volumes, do everything inside Cimerix, and then take advantage of all the other things that Cimerix has to offer. So that's we're using it internally at the moment, and it'll be shortly available to all our clients as well, which we think that's a real step change in terms of the way we can fit in the design process. We've also got a cloud offering coming out soon as well, which again is really there to complement existing license holders, but we feel that people will be able to bring their license and use it on the cloud if they want, or they could just log on and use our software through the cloud. Again, it's just another way of hopefully offering our tools to a much sort of broader audience, and that's our plan. So my contact details are here. So Sean.Horgan at Cimerix.com, sh@Cimerix.com works as well. The thing is, there's a lot of people across the sort of European continent here, from Italy and all sorts. So we have a number of offices around the world, in sort of Germany and India, as I sort of mentioned right at the beginning. We also have a network of great distributors. Again, I think it's always best for you to get local contact, I find. So your distributors are there as well, depending on where you've logged on. So feel free to contact me if you wish, but at the same time, I'm sure you're aware of who your local distributor is, and you can come back and ask any follow-on questions of them too. We always love to see people's applications, and that's the way we show how Cimerix can be so much faster. And that's really the way we go about, hopefully convincing people that Cimerix is the right solution for them, is that running something real. So that was always what we love to do. So if you've got any application you'd like to see Cimerix run on, any sort of turbo machinery application, then please send it to us. get in contact with your local distributor, and we can show you why so many people are moving to Symerix. As I say, we were any of those more specific questions we have, we've got a note of them all, and we'll come back and follow with you individually. You'll be hearing from us, and to address some of those other questions as well. In summary, fast, robust, accurate. That's what Symerix is all about. And so I hope this webinar has been of interest to you. It's an ongoing webinar series that we run. So this is the latest, and we'll continue to do so. It's meant to be educational, but again, also meant to help everyone understand what Symerix is all about. So, but anyway, thank you very much for attending. Thank you for your time. I will bring this session to an end. We'll be in touch, and please feel free to contact us too. Okay. All right. Take care. Bye-bye.